Okay, everybody's up to speed, I hope. And I haven't lost you yet, because this is one of those things, just like every other new subject. If I lose you here, I'm going to lose you through the rest of it, and then you're never going to get it back. So, okay, okay, so the blade angle has a pronounced effect on the mass of air moved as well as engine RPM. So I explained that, that blade angle has an effect on the engine RPM, specifically when we talk about fixed pitch, when we look at that. Of course, it does too on a constant speed. If I pull and change the blade angle on it, it's going to. But I want you to understand that there. So I tell you that to tell you this. There. 1 degree, that's supposed to be a degree. 1 degree of blade angle, 1 degree of blade angle can change engine RPM by 60 to 90. 1 degree of blade angle can change engine RPM by 60 to 90 RPMs.
Wow, just 1 degree? That's
You gotta go out? Sorry, buddy.
pretty big load.
There you go. Sorry, I have a demanding dog. Zeus had to go out. All right. 60 to 90 degrees. Yes, 1 degree. So that's why I say it has pronounced, that's what I mean, a lot. So we go back to that type certificate data sheet, and this is something that I was able to do with my aircraft. So I want it to go faster. And when you are dealing with aircraft, and you guys will be able to do this at a certain point, I have this range of 2470 to 2320. And as long as I'm within that range, I'm completely legal. I can do whatever I want. Notice it doesn't have any sort of pitch or blade angle. It just says it's got to be 69 inches to 67.5 and somewhere within this range. And so if I say to myself, because that's what I say, and I know it's me talking because I recognize my voice, that I want my airplane to go a little bit faster. Well, if I want it to go faster, it means I'm going to need more blade angle or more pitch out of it, if you will. And this number over here is more of a flatter blade. That's why it allowed the engine to turn faster. And this over here, 2320, is more bite out of the air, if you will. If I have more bite, I'm going to go faster, and I'm going to show you why in a second, but you probably already figured out anyway. So if I have my static is 2470, and I can take it to the prop shop and I can have them put a little bit more of a bite into it, that means I'm going to go a little bit faster when I'm flying, because it's per revolution, it's taking a little bit more of a bite. So that was something that I could do. So I had to do the math and figure it out, and where am I, and then how much would it cost, and it turned out it wasn't worth it. But it was interesting to note like what one degree would get me, or one, and you're going to see 1 more inch of pitch, and then you do the math on that, and it just turned out it was not worth it. Oh, so while I'm thinking about that, so why would anybody then want a 2470? Well, we are going to cover this in some note writing, but a lot of props come in 3 different flavors, if you will. So prop A is going to give me 2470. Prop B is going to give me 20. Well, C would give me this. So A is this one, C is this one. There's one in the middle, a B version, that would give me the numbers right between here. So 2470 to 2320, I don't know what's the middle of that, 2400 thereabout. So that's 30 now. Yeah, about 2400. And so this one here, we call it a climb prop. This one here, we call it a cruise prop. And this one here in the middle, we call it an all-around prop. And this is really where most props come in. They're good at cruise and good at climb, but not perfect at either one. And we're going to talk a lot more about that as we go. Okay. So we now know that there is this pitch distribution, and there's this change in the blade angles as you go down the blade. But we haven't really talked about why, because it's moving at the same RPM, obviously, but it's doing a lot of other things that are very different. So the reason why reason why blades have pitch distribution. Reason why blades have pitch distribution. Pitch distribution, twist, T-W-I-S-T, twist. Sorry, you're going to say, what is that word? It's twist. And many different airfoils, and many different airfoils. And when I say that, I mean on the same blade. If I look at that same propeller, down the blade, it has different pitch distribution. It's got that twist to it, and many different airfoil shapes. Some are fat, some are thin, some are the cord is narrow, some the cord is wide. So it moves all over the place. Different is because airfoils is because the blades move in multiple dimensions. And they're all different going down the length of the blade. So if we look at it, number one, we have different rotational speeds. Different rotational speeds. Different rotational speeds of each station. So if we have a blade, and of course here's the hub, and the blade is out here, and it's going a certain RPM. If we're going 2,500 RPM, I could have made that any number. We have 2,500 revolutions per minute, sure, but this blade out here has got to go, as you know, much faster in that circle. If speed-wise, miles per hour wise, it is going way faster miles per hour in a circle than a spot right here is going much slower, right? And hopefully everybody knows that. You know, if you look at a bike tire going around a tire on a, driving down the freeway, and you look over the big rig next to you, the outsider on the outside of the wheel tire, it's going really fast, but you look down here at the hub, and the hub is really kind of moving kind of slow. You can kind of start to make out the words on it and stuff, but out here, everything's a blur, right? Because miles per hour wise, it's moving much faster. All right, 2, forward movement of the aircraft. Forward movement of the aircraft creates different angles of attack. Different angles of attack for each station. And remember, I'll write it here, so remember, angle of attack. Oops, I'm going to try and spell it even remotely right. Angle of attack is the angle between the chord line and the relative wind, and of course, the relative wind is what is relative to that particular station. So if I have an airplane, and unfortunately during this part of the class, I do a lot of hand gestures and motions and so you kind of have to look. So, if I have an airplane and the airfoil is flying this way, my angle of attack is coming right at it. But, you see high performance F-16 jets, so maybe going to high angle of attack, and they're still flying this way. my angle of attack changed dramatically because it's still flying this way. But if you get an F-16 that's going straight up this way, well, then the angle of attack is this way. So it's relative. It's not necessarily the wind, but it's where it seems like the wind is coming from to the wing, or in this case, the propeller. The ideal, I'm going to write just a few things here. I want you to get sort of caught up. Eric, you're looking good. Janet, you caught up? She says yes. Okay, good. She just puts yes right there because it was caught up.
Hey, Kevin, I have a question.
Yeah.
So you said on the type certificate data sheet, you would increase the pitch or the blade angle.
Yep.
In order for you to take a bigger bite out of the air,
right,
and therefore go faster, right?
Yes.
So does that mean more thrust?
Yes.
But see, now the actual question is, but it's going to be spinning slower. So wouldn't that mean it's not producing as much thrust?
You are a very astute guy, and I was almost hoping nobody would notice that, or at this point. Okay, the reason why it made the engine turn slower is because my feet were on the brakes and the relative wind is all jacked up. And I'm going to show you that next. So that slowed the engine down. When I take my feet off the brakes and start the aircraft rolling, RPM is going to pick back up.
So when you're flying, it's actually still going to be around that 2470,
Yep, it's going to be close.
Gotcha.
I don't know if this is a stupid question, but why in like propellers do they not lead and lag like in a helicopter rotor?
I don't know. I don't know. Just don't. Let me think about that one. They do have a bit of an aerodynamic twist to it, but you're not changing what they're doing to the extent that you are with a helicopter. And plus those blades are huge. We're only talking about 2 blades put together that equal 6 feet in most cases. Maybe, yeah. Most blades don't go beyond 6 feet unless you get in the really big props. So it's just a much smaller area.
Okay, that makes sense. Not going to have the vibrations like in a helicopter.
Yeah. Okay. Okay. So what we're going to do is this is going to be one of my more difficult things to explain, but I will do it. Example of why each station is set at a different angle, All right, but I'm going to make a couple notes here before I show you the example. So the ideal angle of attack, remember, angle of attack is the angle between the chord line and the relative wind. Angle of attack on a blade is 2 to 4 degrees. Okay, that's my ideal. 15 degrees will usually result in a stall. Point number 3, blade angles are usually, I don't know why I put usually, I should just put they are. Blade angles are, let's just be consistent, smallest at the tip and largest at the hub. Largest at the hub. All right, let everybody get caught up. shake their brain out, shake your fingers out. All right, Eric, you doing good? He's my man. J-Rod, you're good? Yes, I am. Thank you.
Doing great.
All right, this was pitch. I had another slide that I just went by, and but it's the same thing. We talked about this. This is just pitch. So then, like I was explaining on my airplane, if I wanted to, if I wanted more pitch, I would go faster because it takes a bigger bite. We're going to come back around and talk a little bit more about this, about pitch and how this is figured, geometric pitch and theoretical pitch and things like that. But we're kind of working on something else right here. So this slide, you have to stay with me and keep an open mind on this. And well, the first part is I got to not screw it up because it is a little bit difficult to conceptualize this. But I'll follow along and hopefully I won't screw it up. So I think I'm going to go to this slide. All right. So you're familiar with Pythagorean's theorem. And I know when I said that, you're like, holy crap, this is going to suck. And what this is showing, and if I got the right slide here, let me see. Blade angle 36. Let me see. 20. Yes, okay, I got the right slide. Okay, so what I'm looking at here is the same propeller. So it's the same propeller on the same airplane rotating around. I have, we should have some notes here. Does it have it here? 36 is station 36. No, it doesn't have it. So I need my pen so you guys can keep track of this. So I've got a blade here at station 36. So that's 36. I have a blade station at angle 24, and I have another one at 12. All right. So remember, so if we're going to think about it, then the hub would be over here, right? And so this is 12 inches from here. That's 12 inches. And this is 24 inches to there. That's 24 inches. And this one is 36 inches. So, all right, same blade. So keep in mind now, for every one foot that the plane moves forward, the prop, we're gonna look here at station 36, for every 1 foot, and that's what this represents, the aircraft move forward 1 foot while in flight. And this is all turning the same RPM. So the blade, remember the blade's coming around, so the aircraft move forward 1 foot, and the blade was going the same RPM, and it came down. So for every, I want to say for every 1 foot the plane moves forward, the prop at station 36, it rotates 2.9 feet. All right, and so let me think where we get that. So it rotates 2.9 feet, and the relative wind, this is the relative wind, is going to hit it at an angle of 19 degrees. So I've got to have this twist right there. Let me think about, why was that? So we have
9 feet per second.
What's that?
Is that per second?
No, it's actual. So we're not even using time at all here. So this moved over, I know it is. So this moved over, plane went forward 1 feet. The blade, well, I'll have to come back. Like I said, this is almost kind of hard to even explain to me for sometimes. Okay, so, but I'm going to go with my point here. So the blade, it has to be at this angle right here because of the way it's moving. So, so that gives us an angle of 19 degrees. And we're using, you guys haven't had electricity yet, but we can use arc tangents and tangent and cosines to figure out our angles because it's a right triangle. So if I back up a little bit, this is a right triangle, which means this is a 90 degree here, which means that if I know the distance between A and C and I know the distance between B and C, I can also figure this out because of the triangle. And then I can figure out my angle. So based upon all of that, we can determine that this is in fact a 19 degree angle. And so this blade at station 36 must be set at 19 degrees to meet the wind, the relative wind at the proper angle to not stall. All right. All right, so we move inboard. The plane is still going to move forward 1 foot, but during that time, the propeller itself moved 1.9 feet. And so what do I mean by 1.9 feet? So here's my propeller out this way. How far, so we have right, station 12, station 24, and station 36. So the plane moved forward 1 foot, and this moved forward that far, 2.9 feet. This one only had to travel 1.94 feet. This one only had to travel 0.97. Hopefully you can see that. So I'm looking at in multiple planes. So right now we're just standing in front of the airplane, looking at how far that blade moved. And I'm telling you, just because that's what you have to trust me. I go to another slide here, which does it. There we go. And so during this time, the blade moved forward 1 foot as well. So in this plane, it moved forward 1 foot. And in the other plane that I just showed you, back a little bit, it moved this way. So that's what I'm showing. So this right here is this distance, C to B, B to C, and move that far. And then it moved forward 1 foot because it's attached to the aircraft, and the whole aircraft moved forward 1 foot. So using Pythagorean's theorem, which is a squared, this is a, this is b squared. A squared times b squared equals c squared. It's that distance. You finish that off. You use your arc tangent functions with trigonomic functions, and you get this angle. So if you don't quite grasp that because you haven't electricity yet, or you had electricity and you totally didn't know what I was talking about, don't worry about it. All you can just trust me on this is based upon doing maths. We have determined that this angle has to be 19 degrees. And we've determined that this angle must be 27 and this one must be 46. So if you can see that, this was a little bit flatter. This has a little bit more pitch, and this has a whole bunch of pitch. And if we take that and keep that kind of put into our mind real quick and say, okay, so the root had a whole bunch of pitch. The middle had not as much, but more pitch, at 46, 27, and 19 degrees. We look at that and we think, is that true? And I could say, why, look at that. Back here, we have all of this pitch. It gets less. By the time we got out here, we only had 19 degrees. Was it 46, 27, I think, and 19? And so you look at that, that's why that is. Because as it comes around, because of this and the other function, you have different angles of attack. And if we kept everything the same, so if we said, well, let's make everything 46, well, then fine. Then this is at 46 and this is at 46. And I could do the math, I'm not going to, and say, whoa, this is the relative wind coming up. That's going to stall. That's going to stall. And we get a little bit of thrust then in this part of the blade. And that's all the thrust I'm going to get is down there at the root, which really has the least amount of thrust anyway, just because of it's moving slower and everything else. So that would not work at all. So that is why you have to have this twist so that you actually have the proper angle of attack, because the blade is moving in 2 dimensions. And I hope that I didn't just break you. Let me see.
Not gonna lie, you kind of just did.
What's that?
Kevin EXC not responding.
Oh my.
Okay, so I don't necessarily want to write all of that because I have notes here that I can follow, which I didn't anyway. So what does it show? Yeah, blade, I'll just go back to what this was. My notes are simply, using Pythagorean theorem, we can see the following. A shows the blade at station 36, B at 24, and C at 12. I told you that. Back to 36. For every 1 foot the plane moves forward, the prop at station 36 rotates 2.9 degrees. And I explain that. The relative wind hits the blade at an angle of 19 degrees. Blade angle must be somewhere, so the blade angle must be at 22 degrees in order to keep the angle of attack at 3. Remember, we want 2 to 4 degrees angle of attack. So if the wind is at 19, then this should be at 22, right? So we get a 3-degree angle of attack. Same thing over here. It rotated this, that 27. So that should be at 30 degrees to give us 3-degree angle of attack. And then 46 is where the angle of attack is. So the blade should be twisted to 49, right? 49 degrees about. So that works. So now, here is the thing that will screw you up. So, not you, you're going to get this. This is what screws up the prop. This is all fine and well. This works absolutely great. And now we're going to go back to what Orville and Wilbur were talking about. What happens if I increase the RPM even a little bit? Well, if I increase the RPM, then this number right here is going to go up, and this number is going to go up, but they're probably not going to go up in a way that keeps the triangle perfect. It's going to change it. This RPM may go up, so now the blade is moving like 3 feet, but we may only go 1.1 foot forward. Well, when we do that, that's going to change the whole way the triangle looks. The relationship is going to change, which then is going to change the length of the hypotenuse. And if it changes all of that, then it's going to change the angle, and that becomes something different. But what didn't change? What is the one constant in this whole picture? Did anybody tell?
The blade angle.
You got it. The blade angle never changes. So when I'm sitting on the ground, and I'll bring up another slide here. When I'm sitting on the ground, there we go, sitting on the ground, this is what this is representing over here. So when I'm sitting on the ground, and here's the nose of the airplane, and it's rotating, and we're just going to look at BC right here. When this is rotating, and yet the plane doesn't move anywhere, here's my angle of attack, right? It is, it's horrific. So here's the direction of the relative wind is coming up right into here. And I've got to stall. It does not work well. But yet when the airplane starts moving forward, because this represents the triangle right here.
Hate to interrupt, but your pointer's white, so it's kind of hard to see it.
Right there? Should be red.
The actual dot itself is white. I don't know if anybody else sees that.
Well, we'll change it.
I think that's just you.
Okay, so this represents the triangles we looked at before, but yet there's 2 triangles on this page. Now I need a pen. Things that actually screw me up and make my life hell. So I'll do it in red. Here's one triangle. Here's a triangle right there. And it just kind of goes, there's the length of it. So the hypotenuse basically goes from here to here. And that's like the world's worst triangle because one leg is only like that big, you know? And so it's just this terrible looking triangle. And then here's the other triangle. It's really not a triangle. It's just a line. Now this one, here's a triangle where it's still, this is the prop rotating. This is the forward speed of the aircraft. And now we're back to here. And that looks like the triangle we had in the last picture. Now we can actually get some sort of angle here and say, well, now we know how the blade should be fixed. And so at this speed, whatever this is from here to here, the prop is perfect. It's got a nice 3-degree angle of attack and oh, she's working sweet. Speed up a little bit and it's going to go from 3 to 2 degrees. Getting outside of it, speed up a little bit more, it's going to go 1 degree. Hey, that's not very efficient. All right, we go back here. We've got, I don't know, somebody, what do you think that this angle is right here?
Houston.
What's that?
Houston.
I can't hear you. Erase. So this angle right here, was that 45 degrees? Yeah, it's about 45-degree angle, I'd say. Anybody care to What's
30,
that? What's that?
30 degrees, I think, not more, not more than 30.
30?
Yeah.
Okay, 30 degrees. So 30 degrees. Is 30 degree, how is that going to work when I'm supposed to have 2 to 4 degrees? So I've got a stall here. This is just stalling. It's not doing anything. So it's like a big paddle in the air that's not doing anything. It's just whacking the air and slowing the engine down, which is why you have the slow RPM when you get into this static RPM, which is what this is, static RPM. No thrust, just a paddle whack in the air. All right, so this over here to the right, and I'll change it to a laser pointer so that Zach doesn't get all upset with me. So that's what this represents. Again, it's the same thing here, just brought over here. So when the aircraft has got the brakes on, here's my angle of attack. It's horrible. Here I am I release the brakes and the aircraft starts to roll forward. And hey, look at that. I'm starting to get some forward momentum and my angle of attack now gets more reasonable. Still not that 2 to 4, but hey, let's just say it's 10 degrees. Hey, prop can work with 10 degrees. Now I'm starting to get some real thrust out of this thing and it starts going faster until it gets up to its optimum speed where the prop was designed for. And I have a nice 2 to 4 degree angle of attack, which I guess I could tell you all that to tell you, if you think it through, this propeller that is a fixed pitch propeller and the pitch never changes really is only going to work very well and very efficient in a very narrow range of operation. The RPM must be at the exact designed RPM while the aircraft is moving forward at the exact speed that the aircraft was designed to move forward in. So if we can take my little 150 and let's just say I spent $100,000 on it and I put speed fairings on it and I put, wheel pants on it and fair them all in and speed tape everywhere and super high Teflon polish all over it and make it so it's the slipperiest 150 ever to roam the skies.
And 5 knots.
And now it goes faster than every other 150 in the world. My prop is going to be horribly inefficient because it was never designed to go that fast. And I got to get a different prop. So that's why I don't do that, by the way. Okay, so MJ had a question. Are the 29, 19, and 0.97 feet given, or is that calculated? In that example, it's a given. It's a given. But it was based off a calculation. Pretty sure engineer figured it out. Yeah, he's right. Engineer figured it out. So, okay. Hopefully you understood that. And what is the takeaway of this? Well, the takeaway of this is, number one, props are only efficient in a fixed pitch props are only efficient in a very narrow range of operation. Maybe I could write some stuff here as I think about it. Let me see.
Kevin.
Yeah.
I have a question if you go back to the slide.
Okay.
So is that showing the same area of the basically airfoil of the propeller?
Yes. This is the exact same area as the aircraft starts to speed up.
Okay. So it has a little bit of elasticity then, right? To get to that angle too.
No, the angle never changes. These angles should be exactly the same. So it's just this picture 3 times, just a bad picture, but so it's 3 snapshots in time. Okay. So I could cover these 2 up and say, this is with no forward motion. Now get rid of this one and get rid of that one. Now we're just looking at this one. This is with it moving forward, but not at the right speed. And then get rid of these 2. Now we're looking at this one. Here it is finally operating correctly. Silence.
Okay.
Which is the same as this one. It's 2 snapshots in time. So this is with the airplane not moving. This is with the airplane moving.
So what change is the angle of attack, right?
That's it. The only thing that can change is the angle of attack. And that's what I'm trying to explain to you is how they developed the twist, why it's there, and what it means to not have it.
Yeah, but in some other areas, it's going to be working fine because it's got the twist, right?
Yes.
But not in that particular one.
Well,
at some speed.
this picture here, one more, is looking at one blade station only. It's only thinking about one blade station. If I go back here, this is one prop looking at 3 blade stations at 1 fixed RPM at 1 forward speed. So this is, remember, this is the same propeller, 3 places on the propeller. That's why place number 1 has to have 19 degrees, place 2 is 27, place that one is 46. And I don't remember what this one was. Okay, so this is doing the same thing. It is just a different variation on the same principle, explaining it a little bit different. So example 1, it's this propeller, 1200 RPM on the engine with no forward speed at all. So I've got a 20-degree angle of attack. Horrible angle of attack. It's, again, just a paddle. It's an inefficient wing. It's stalled out. It's just causing drag on the engine. It's my static RPM. I take my feet off the brakes and I start to roll forward a little bit. I have not changed my RPM, but I'm going forward at 50 miles per hour. Not very fast for an airplane. And I have a 0.8 angle of attack. Still horribly inefficient. Not a good spot. But I get this propeller where it should be at 1500 RPM, which is very slow for a prop. I don't know why they picked that. Moving forward at 50 miles per hour, a very slow airplane. I have 4.4 degrees, which apparently is acceptable in this range. But again, this is the same blade station on the same airplane, the exact spot, 3 snapshots in time. Static RPM, 1200 at 50 miles per hour forward and 1500 RPM at 50 miles per hour forward. And it kind of helps you, maybe I should have started here because you can see where you get the triangles from. And then you just do the math to get the arctangent to get that right there. All right.
I think that picture helped me the most understand.
Good. I'm glad I went back to it then.
I like how they spelled attack.
Attach.
Oh, it's British. I wanted to go to this. So what are my takeaways? Because I know there's several of you going, okay, do I drop the class now or what? How bad is this going to get? So this is what I'm just going to make up some stuff here. Some takeaways. So takeaway. You guys got to help me out here. A fixed pitch prop is only efficient let's say in a narrow RPM and forward speed range. Otherwise, it's just really inefficient. What else? The prop is twisted. It twisted to keep the correct angle of attack, on each station. And you could just believe me, I suppose. And if you're fine with that and just believe me, go, it's twisted for that. You're fine. You're fine. But I wanted you to know why it is and prove to you that. And so if I lost you on all of that and you absolutely just lost your mind on it, you're going to be okay. You just have to trust me and know that that's true. And if you can trust me and know that that's true, I think you'll be fine.
Is the math question like that some shit the FAA is going to pull on a test?
No, if it was, I would start running the math through you. We do have a math thing that I do in lab, but it's not like that. I don't make you figure any of that crap out. It's just explain to you why it is. Just like I'd explain to you why the paint is black.
Perfect.
So I think that's my good takeaways there. So I had points 4 and 5. I don't really need them because an example of an aircraft 150 miles per hour, oh, I guess it was not relevant, but I didn't tell you that. That example, the aircraft is going 150 miles per hour at 2,000 RPM. That's what it was, but that's not really relevant. Okay, so that means that I'm at 0.6. So maybe I can try and keep my thing here. So see the angle of attack, angle of A, will change with, I guess it's kind of a takeaway, with any change in RPM or aircraft speed,
And that's per station, right?
Yep, everywhere along the entire blade. You change RPM, you change aircraft speed, you just change angle of attack on the whole blade. That'll make this 5. So fixed pitch, props. Probably didn't need to write these 2 points up here, my takeaways, because I think I'm writing them here. Fixed pitch props are typically designed. I don't know why I write typically, because it's just, they are. I don't know. I add words in there, sorry. I guess it's a qualifier just in case somebody wanted to prove me wrong. Well, I didn't say all of them. For optimum efficiency at a narrow set of parameters, at a narrow set of parameters. And then again, and I already mentioned this once, ideal angle of attack is 2 to 4 degrees.
Is that ideal angle of attack?
Yeah. There. August. His dogs can hear my dogs. I have to let my wife know. You're starting a bark. I always yell at the dog, don't start a bark. I do have some other notes here, and I'm not gonna write them. I'm gonna tell you what they are because really, I think it's just a little extraneous. Let me see. It does deal with a certain PowerPoint. Let me see. I believe it's this one here. So the points that I have written on this one are: note the difference between the angle of attack when stationary versus in flight. So on the ground, the propeller moves from A to B. All right, let me get my laser pointer. You know, last class, I had some guy, Steven, sat in the back and couldn't see it if I used it. So the blade moves from A to B, and the angle of attack is very inefficient. In flight, aircraft moves from N to O, moving forward, and that much. Yeah, extraneous. I don't need to talk. Yeah, we already covered this. I don't need to bore you with it. I also wrote in a dive or a climb. Well, of course, if we start to climb or start to dive, that changes everything too. So an extremely steep dive with high speed, well, the prop doesn't really know that it's in a dive. All it knows are 2 things. Knows angle of attack, and the angle of attack is based upon speed and RPM. So of course, if I go into a dive, well, that's going to significantly increase from here to here, which could actually put me into a negative angle of attack. If you go into a climb, then you are going to slow the aircraft down, which moves the triangle the other way. So, and that increases the angle of attack. So these are all just points to think about, which I don't feel like I need to write because I sort of covered it. Oh, not this page. All right, so it is, I'm going to move on to another point, but I think rather than just starting a whole new point, I will leave that up and we can go have some dinner.
Yep.